Okay, in last lecture, we were discussing about the probability. We discussed about addition rule of probability. When you do one trial, like in a single trial, you look for few options that you have to choose or select something from a sample space. And we have seen different kinds of probability, like in terms of classical probability that we will be going to use the most, like the number of favorable outcomes that you are looking for from the total number of sample space. So that is called classical probability. And the one is empirical probability, that when you have done some experiment and you're observing something to that experiment, that is called empirical probability or observed probability. And one is when you have no data and you just make your educated guess that whether it's going to be true or not, just like an iPad. I gave you an example that the Mac was producing iPad without knowing that whether will it be working or not. So that is called subjective probability. Like it is based on educated guess with various reasons that whether will this product will work or not. Hold on, my screen has stopped sharing. One second. Continue. All right. Right. So we discussed addition rule for probability. Like let's say we are rolling a die and we are looking for two options. Let's say, what is the probability of getting a 3? Or what is the probability of getting a 5 from a single trial? So that is called, then we use the addition rule, where we discussed about, in English word, it is called or. Like whether this is going to happen or this is going to happen in a single trial. So we are going to write it in this form: probability of A or B, like A event or B event. And then we discuss it that how did we calculate this probability, that we add these probabilities of each events, probability of A and probability of B. And then we do minus probability of A and B. So why did we use this probability? Because I gave you one example last time when we were discussing about the victim, whether he is guilty or non-guilty, he did it or never did it, because we are uh, deleting the double count from that experiment. Because you have seen that 72 and then 72, we are double counting it. So due to that reason, we have to delete one common number that is occurring in both of these experiments. So this is why we use this probability of event A and B. Like this event A and B occurred in a single trial. We are talking about single trial, like whether this is going to happen, like let's say we are talking about odd numbers of probability of 3, or even probability. If you are rolling a die, whether you are going to get even number or odd number from 1, 2, 3, and so on 6. So it cannot happen at the same time. So this means we are going to discuss it. That is called mutually exclusive events. So that and is, so this and means where we are going to discuss the probability in a single trial. So this and has different meaning. Today we will discuss the same thing, probability of A and B, but in terms of another thing, like that thing we discuss in a single trial. Now we will do multiple trials. So when you do multiple trials, multiple experiments, so then we need to use the multiplication rule, not an addition rule. Then we are not anymore that in addition rule, we are in the multiplication rule when we do multiple trials. Like I'm rolling a die first time, and then I said, okay, rolling it. Like if I'm saying, okay, what is the probability of getting a 3, or probability of getting a 5? If you are doing in a single trial, then it cannot happen at the same time. But yes, when you do double time, probability of selecting 3 from rolling a die, and then you roll another time, which is called probability of 5. So then it can happen when you do successive trials. When you do triple trial, multiple trials, then it can happen. So then that thing, so this thing we will discuss now, that probability of event A and then B. It means here we will use then. After A, we are going to do another experiment B. Just one key point you need to know here, that when we use the multiplication rule, so this is our first event when we will be writing first event, like this is first experiment we did, probability of A and B. So this will be our second trial, second event. And in a second trial. So this, so here we are using, so this is why we are saying probability of A happen, and then we look for probability of B occurring in a successive trial. Then we are looking for probability of B in a second trial, or it can happen, I will be doing another trial C and A, B and C and so on. So this is how we will use the multiplication. So let's we see these things in few examples. Let's say I am going to drive. What is the chance that I am going to drive BMW? Well, this is not happening. So we are just saying, let's say, what is the probability that I am driving BMW? I just need an answer of whether this is going to be true or false. So I need to choose one from these. So this is another question. So this is first experiment, like first trial. You are looking for that whether I'm driving BMW. So the answer has to be from true and false. So it means if it is true, so well, this is false. So if you are looking for the right answer, so then false is the favorable outcome of false is has happened only one time in it, by either true or false. So the probability is 1/2 because number of sample space is 2. We have just two choices to choose from, true or false. So this is first trial. Second trial is that I am going to look for what is my favorite color. So, well, my favorite color is blue. So I like blue. So, but how many choices I have? I have 5 choices in it. So the correct answer is true in that, blue in that. So this is my second experiment. So I'm going to call it second trial. So let's take a random guess. I am going to find out what is the probability of getting both of these trials correct. What is the probability that I am going to get the answer for both of these trials correct in it? Like I am not driving BMW and my color is, the favorite color is blue in that. So how can you choose it? So we need sample spaces, like how many options I can have at the same time, like in the first experiment and in the second experiment. So how many choices I can have in these two experiments. So the answer to this is because whether I'm driving BMW, it could be true or it could be false. So how many options you can have when you combine those two experiments together? So the second option is to make the second experiment correct. So you might have, the option is because these are all have equal chances to be occurred, red, blue, green, and in the sample space. So you might have, if you choose true, then you have choices to true A, true B, and true C, and true D, and true E. These are the choices we can have when we combine them together. So if you choose false, so then again, for alls, you have 5 choices to choose: A, B, C, D, and E. So when we write it in a sample space, so this is how we will writing. If you have true A, true B, true C, true D, true E, and then false A, false B, false C, false D, and false E. So it means how many number of choices I can have if I combine both of these experiments. So there are 10 choices I can have. But if you are looking for the probability of both of these answers right, so there is only one option in it. So that is what that I have. I am not driving BMW, and other is that my favorite color is blue. So the option is false and B. So this is the correct option. But it is occurring in this sample space only one time. If you're looking for this option for probability of both of these answers right, so this is going to happen only one time in the number of sample spaces. So this is one, because this is how we will use a classical probability, the number of favorable outcomes divided by the total number of sample spaces. So this is occurring one in our sample spaces divided by the total number of sample space, which is 10. So this is how you will look for the probability of one event in multiple trials. So this is one experiment. I'm going to lead it to in another direction, then we will look for something else. So the second example is I have given last time that for finding a victim, that whether this is that person is guilty or non-guilty, this is what we used last time. So if it didn't happen, then 11 people were guilty and did not do anything. 72 people, they did something wrong and they were found guilty, and 85 people didn't do anything and they found non-guilty, and 9 people did something and they found non-guilty. So if I am looking for probability of selecting, but this is one experiment, I am going to look for probability of selecting guilty, and then I'm looking for probability of finding something else, non-guilty. So it means in a single experiment, I'm looking for two options. I'm looking for probability of two options, one after another. Like first time I will look for probability of finding a guilty. So how many people are guilty in this column? Which row I will be looking for? Guilty is this one. So this row is telling me how many number of people are guilty, like 11 or 72. So when you add them together, so how many people will it be? 83. So total number of people divided by total number of people, how many sample spaces we are having? People who are guilty and people who are non-guilty, we are adding them together. 11 plus 72 plus 85 plus 9. So this will be, what was the value? I think all together 177. So it means probability of finding guilty people were 83 and 177. So what is the probability of finding one guilty person from all of these people? So this is the probability of finding a guilty person is 83 by 177. So this is the percentage that I can find the guilty person from all of these people. So let's say I found the one guilty person and I'm putting him in the jail. So that person is going to a jail, like one person. So it means how many people I'm looking for here in this experiment? 2 people, like guilty and non-guilty. So it means if I'm looking for 2 people, so I need to have 2 trials for that. So when I found one guilty person, I put this person in a jail. So the rest of the people, how many it will be? From 177, if I am putting one person in jail, so the rest will be 176. So then from that sample space, like from 176 people, because now we are using and then, now we are going to do second experiment after that. So it means without replacement. I'm not replacing that person back into the same sample space. So I'm not keeping him again as a victim. He is proved guilty, so I'm putting him in the jail. So the rest of the people will be 176. And from those 176 people, I am finding the person who is not guilty. So how many people are not guilty in this experiment? So this is my non-guilty row. So this is going to tell you who didn't do it and who did it, but they are finding non-guilty. So 85 plus 9 will be the total number of people who are finding not guilty. So 85 plus my 9, it will give you, what will it be? 90, 94. Overall, how many people? 176. So it means if I am going to do an experiment without replacement, like I'm not putting the same, finding one person and then I'm putting him in the jail. So then this is going to affect my second event, second trial, because it is reducing, it is making the sample space down. One amount will be less from the total number of sample space. So it means probability will be dependent on my previous experiment. So this is the without replacement experiment. So this thing that if you are finding one experiment and then after another, and because this thing leads to what? So this experiment leads us to the conditional probability. So conditional probability means when you do some experiment, given that some event has already happened. So give conditional probability means that the probability of one event is happening given that one experiment has already happened, like finding a guilty and non-guilty. Like, so we will be writing in this way. So in this case, when you are writing probability of, this is the symbolical representation of probability of B given probability of A. So that means we are going to read this vertical line represents here given that probability of finding an event B. So this is my second experiment. From second experiment, I'm looking for. And given that, like vertical line, so this means given that probability of A finding first event or first trial has already happened. So now you need to know both of things. In our first definition, when I was going to use probability of A and B, so A was first, so that was from our first experiment, and B, so B was our second experiment. But now this, when you do successive trials, so then this leads to the conditional probability. You need to find out whether my second experiment is being affected by the first experiment or not. So there we need conditional probability. So there is a condition on it that what has happened before and now what is happening. So probability of finding, so this is how you will write the conditional probability. So this means probability of event B occurring given that probability of A or A has already happened. Like in my last example, this one. I need to find out in the second trial probability of not guilty person given that probability of finding given a guilty person has already happened. So this is what we need. So this is the same thing we are representing in conditional probability, because here we have done two experiments. So second experiment is after the first experiment. When you do some experiment after the first one, there we need conditional probability. So this this depends on two conditions, whether these two experiments are dependent or independent. We are going to discuss it in 2 minutes. So this is how you will write the conditional probability. So here you need to use it, the finding a not guilty person given that probability of finding a guilty person has already happened. This is how you will write it down. So now you need to know one thing. So in this example, so is it going to affect, like probability of finding not guilty person, has it been being affected by finding the probability of a guilty person? Like, is there any effect of the first experiment on the second experiment here? So the answer is yes. Why? Because in the first experiment, you have total number of people. How many? 177. But then when you find one person who was guilty, I put him in the jail. So the rest of the people were 176. So it is being affected by the first experiment. So this means because it is going to reduce the probability of finding the second one, because your sample space is becoming less and less and less. So this is how the probability will being affected from the first experiment. So this kind of experiment is dependent experiment, because second experiment is going to depend on the first experiment because it is reducing the number of sample space. But when you look this example, the first example, that whether I'm going to drive BMW or I'm finding what is my favorite color. So these are two different experiments. Does it has anything to do these two choices has anything to do with the second choice. Like, so there is no effect on it. Finding that whether I'm driving BMW has no relation with what is my favorite color. But these are two experiments I am going to do. These are two choices I'm looking for from two single experiments. So this means these are called independent events. Sorry. These are called independent experiments or events or trials. These independent events or even independent trials. So, so independent is just like you used in English, that I am an independent woman. I am an independent man. I am not relying on anything else. So this is the same thing. You find the probability like, okay, so one experiment is not being affected with the second experiment. But if you find the dependent experiment, like finding a not guilty and guilty person, so these are being affected because it is reducing our sample spaces. So this is called dependent events. So this is what I have explained here, independent and dependent events. So independent events, the occurrence of one event does not affect the occurrence of another event. Or you can write it down that A and B are two independent events if the event of A happening does not affect the probability of finding B is happening. Like probability of finding whether I'm driving BMW has no effect on probability of finding what is my favorite color. So these are independent events. So if the experiment is not independent, for sure that will be dependent event. So this is what I have mentioned here. So another thing. So if you have independent events, like in our first example, I'm going back again to this slide. Where is that? Sorry, this one, first experiment. Okay. So in this experiment, if I look at as just one experiment, the first one, what is the probability whether I'm going to drive BMW or not? So there are just two options. And the answer is only one is correct, which is false. So the probability of, in this case, finding a false from the given experiment is 1 divided by 2, because I have two options and the answer is 1 is correct. So probability of whether I am driving BMW or not, so this is 1/2. But I'm looking at two separate events. So second experiment was finding the favorite color. And how many choices I am having? 5 choices I am having. So if you are looking for 5 choices, so this is how you will write it down. So the answer is only one is correct, because my favorite color is blue. And how many options I am having? 5 different colors. So the probability of this thing is, so this is probability of my favorite color. This is 1/5, right? So if I am going to look for these two experiments together, like if I'm doing second experiment after the other, so what is the probability? What is the probability of finding my favorite color, given that what I drive? So it means this has happened. So what will be the probability? Because these are independent events. There's nothing to do with the first experiment. So what will be the answer if you look at combined together? So what is the probability? So here, actually, in the conditional probability, he is going to ask you about this one. You are looking for this one. What is the probability of this event? So that is other thing. This on your right hand side. The first event is another thing. So you are looking for here probability of my favorite color. So it has nothing to do with what car I drive or not. So it will be the same as the probability of finding my favorite color. So this will be 1/5. So if I look these two statements together, that what is my favorite color, or if you look for what is the probability of finding my favorite color, given that first experiment has already happened. So the answer is the same, 1/5, because there is no other options, right? So it means these two are together. These are the same probability of finding the color. So this means these are equal. So if the same thing is writing it down here. So if your experiments are independent, if A event has nothing to do with the event B, then probability of B given A equals to the probability of B. Like my favorite color. B was my favorite color and A was what I'm driving. So this, because these were independent events, so their answer was the same. So it means the answer will be the same as finding the probability of B, the second event. So if you need to just keep this in mind, that if your events are independent, if your trials are independent, then probability of this conditional probability equals to the probability of B you are looking for. So this is equal. Again, for you, I'm going to write it down so that you guys just, these things, it should be in your mind that which one was our first experiment, which one was our second experiment. So if this is probability of A and B is written, so this means this is our first trial or first event I'm looking for. And this will be our second event. If it is written like this, A, B given A has already happened. So this is our first event that has happened already. And this will be our second event, which is what we are looking for in successive trials, right? So this is why in this one, probability of finding B when this was independent, my favorite color was the same because I had still 5 options to look for my favorite color. So this was equal to 1 by 5. So this is why if this is independent, this will be equal to probability of B. Is there any question so far? Is everything is clear? Okay. So now I'm finding there are some examples we are looking for. Let's say we are rolling a die. Rolling a die has one thing is good. When you do successive trials, for instance, I'm doing one experiment. I roll a die and I found 3 in that. So what is the probability of finding 3 from the first roll, first experiment? That is 1 by 6. So you are not replacing it back. You cannot take it out from the die. So it will be there always, even if you do the second trial. So when you do the second trial, what will be the probability of finding another option? In this example, we are looking for 2. So still the probability of looking for 2 from the second experiment, what will be that one? This will be 1 by 6 because 2 is occurring only one time, divided by the number of events we are having, the total number of sample space we are having, 1 out of 6, because this has 6 faces, and even you do third time, the total number of sample space will remain the same. So no matter how many times you are rolling a die, the probability of finding each event or each number will be the same. So first event, so in this case, in this example, we are looking for probability of 2, given that probability of finding 3 has already happened in rolling a die. So that means we are looking for we are in a second experiment. We are looking for here probability of 2, given that probability of 3 has already happened. So this is because rolling a die giving you independent events, there is not, the number of sample space will remain the same. You cannot take out the numbers from that. So this is why because these are independent events, so we are using the same formula as we used here, probability of B given A equal to probability of B, because these are independent events. So this is the same thing, probability of finding 2 given 3 equals to the probability of 2, because these are independent events. So probability of 2 in rolling a tie, what will it be? Because 2 is happened only one time, so 1 by 6 will be the answer. So these are independent events. In a second example, we have a deck of cards. So we will be doing 2 experiments. One is with replacement and one is without replacement. So in the first experiment, we are looking for probability of finding a queen, given that probability of finding 9 has already happened, but we are using with replacement. For instance, these are the deck of cards I'm having. These are the deck of cards. Let's say I'm looking for probability of finding 9 in that. So I have, because there are 4 symbols we have, one was deck, one was diamond, club, and spade. So how many 9 I'm having? Because each card has 13 number of cards. Each club card is 13 and diamond is 13 and all other are 13. So if I'm looking for 9, so there will be 4 9 in that. So let's say I am finding 9, let's suppose. So how many number of 9 I am having? How many number of 9 I am having in deck of cards? 4. So let's say I find 4. Probability of finding 9 is 4 out of how many number of cards I'm having? 52. So 9 by 52. And I found this card, but I'm putting it back again in my card. This is my one experiment happened. I found the probability of finding 9. So I'm putting it back again. Again, total number of cards will be 52 because it is not going to affect the sample space. Now I'm looking for what is the probability of finding a queen. So how many queens we are having? One for diamond, one for spade, one for club, and one for the other. So finding a queen. So let's say this is the queen. So I'm finding the probability of queen from 52 cards. How many cards we are having probability queen is 4. 4 out of 52. So this is what we will be writing here. 4 out of 52 because we have done experiment with replacement. I'm putting the card back into my deck of cards. So the number of sample space will remain the same. But in a second experiment, we're looking for probability of finding a Q, given that probability of finding 9 has already happened, but with replacement, without replacement, sorry. So if you are doing probability of finding a 9 without replacement, where is that 9? Let me see. Let's say this is 9. So these are total 52 number of cards I'm having. I'm finding the probability of finding 9. So this 9 I took out. So what is the probability of finding 9? 4 by 52, first trial. So I put this card back into my pocket. I'm not putting it back into the deck of cards. So then how many number of cards I'm having? 51, because without replacement. Now I'm looking for what is the probability of finding queen in these deck of cards. So because Q is still there, that was 9 that I took out. So the remaining will be, queen will be the same, 4. So 4 out of 51 because that 9 is in my pocket, now not back into the deck of cards. So this is the experiment of without replacement. This is how you will find the probability of something given that something has already happened. Okay. So next thing is, this is interesting. One second. Probability of, here we are looking for probability of queen, given that probability of queen has already happened. Again, we are looking for 2 options. Again, I'm putting 9 back into my card. It has nothing to do with my previous experiment. So now I'm looking for probability of queen, finding queen, given that probability of finding queen has already happened. So let's say this is my queen, and which is queen heart here. So probability of finding queen, how many queens, total queens. It is not asking you queen or which one, but it is just asking what is the probability of finding queen in this 52 deck of cards, first experiment. So I'm finding it and I selected it, which is 4 by 52. And I'm putting back into, again, this deck of cards. So the number of cards will be again 52, right? Now I'm going for second experiment. Again, I'm looking for queen. So probability of finding queen from out of 50 cards, 52 cards. So this is with replacement because I put back into the deck of cards. So this will be again 4 by 52. And then the rest you will be doing some simplifications, which is 1 by 13. So approximately the very less chances you will be having point something, zero something. So the very less chances you are having for finding a queen from the deck of cards first time, and then probability of finding a queen from the second time with replacement. Now I am doing another experiment. This is nothing to do with the first trial, successive trials, without replacement. What is the probability of finding queen? Here's my question. Probability of finding queen, first experiment. What will be this probability? 4 by 52. So now I'm putting this card back into my pocket. The rest of cards will be 51. So again, I'm looking for queen. Where is the queen? So where is the queen? I'm having less queen now. So this is the queen again. So I'm looking for again queen from the rest of the cards. So what will be the probability of finding a queen? 3 by 52. Why it is 3? Because that queen I took back into my pocket. Due to that reason, the sample space is decreased 51. So the rest of the queen are 3 in that. So again, we are looking for probability of finding a queen. So this will be 3 by 51. So it means that one is the queen card. So queen is also less and number of sample space is also less. So this is 3 by 51. So this is without replacement experiment. So again, you can ask like for this thing, okay, what is the probability of finding queen and then queen and then queen? Like if without replacement in the you can be asked this thing, like what is the probability of finding queen, given that probability of finding queen has already happened, and given that you are looking for probability of finding a queen. So you have rest again, number of sample space will be 50, not 51, because these are two cards you took out. And I am finding again, okay, what is the probability of finding until unless you are getting 0? So there will be only 4. If you are finding 4, so that will be 0 after that. So this is how it is happening. So the next example, drawing a cards. Again, I'm drawing a cards. What is the probability of finding a heart card, given that probability of finding jack diamond? There is only one diamond jack in the total number of 50 cards. So which is, I separated it. Let me see. It's hard to look for. Yeah, this one. So this is called jack and heart card. So this is a jack and heart card I am having. So what is, so this question is probability of finding heart card, given that probability of finding jack heart card, which is only one in that, with replacement. So that in these 52 number of cards, I'm looking for the probability. The first experiment was jack heart card. So it is with replacement, I'm putting back into my sample space. So it has nothing to do with my sample space. Sample space will remain the same. So if you are finding the probability of heart in the second experiment, so the heart is total 13 cards. So 13 by 52, because this is with replacement, I'm putting back into my sample space. So the next one is without replacement. If I'm finding the probability of heart, given that probability of jack heart diamond has already happened. So this, in the first experiment, I found jack heart card, which is 1 by 52, and I put it back into my pocket. So the rest card will be 51. So the probability of finding a heart card, how many cards heart card we are having, which is 13 by total number 51. If I'm going to ask you, think about it. If I'm going to ask you, what is the probability of diamond, given that jack diamond has already happened without replacement, like so this is the jack diamond without replacement, like I'm putting in my pocket after finding first one. So what will be that? Could you think of it? Yes, 12 by 51, because the first one was diamond and total number of diamonds are 13, and you are putting in your pocket, so the rest diamonds will be 12. So 12 by 51 without replacement. So this is what all it means, conditional probability. So this leads to the general rule of multiplication rule. So it means if you are doing successive trials, probability of A and B and then B, this is not addition anymore, because in addition, we are looking for probability of A and B in one single trial. In single trial, we are looking for in addition rule, but here we are doing multiplication. So it means probability of A and then B. So what will it be? We are writing it down generally, probability of A multiplied by probability of B, given that A already happened. So remember, A is our first experiment and B is our second experiment. So it means you have to take the product of probability of A and then probability of finding B, given that A has happened. So this leads to two things. So whether these two events are independent or dependent, as you have seen in the deck of cards, that if these are dependent, so which one is, if you do without replacement, like you are putting in your pocket, so this is dependent on my second experiment, because number of card is becoming less and less and less, right? So this is going to affect. So in that case, we will be using this formula, which is the first one. If this is independent, like I'm putting finding Jack in these deck of cards and I'm putting back into my sample space. So this has nothing to do with the first experiment, because the total number of cards still remain the same. So then in that case, probability of finding another event, second event, will remain the same as in the first experiment. So this will be, you are writing it down, you are taking the multiplication of these two rings. Remember, we were discussing about in the first example that we have two experiments. One was which car I'm driving. So I had two options, which was true and false. Let's go, let me scroll down again. Where is it? This one. So in this case, you have seen in our first experiment, which car I am driving, what is the probability of finding true or false, which is 1 by 2. Second experiment, what is my favorite color? So which is 5 options and 1 is true. So 1 by 5 in that. So if you look both of these correct at the same time, so what was the probability? 1 by 10. So if you look at closely, so isn't it actually you're multiplying 1 by 2 with 1 by 5? So it means probability of A, this is my first event, first experiment, and this is my second experiment given A, but this is independent. This is why probability of B given A equals to probability of B, which is 1 by 5. So it means you are going to take the product of these two probabilities. So if experiments are independent, if these experiments are independent, so then which one will be true? So this is the true, because probability of B given A is equal to the probability of B, just like as our first example. So this is what the general rule of multiplication rule. Now look at some more examples of dependent and independent events. Let's say we have uh, a bag of balls or marbles, we can say. So in this case, if you look at this example, we have 5 total marbles or total balls we are having. 3 of these balls have red color and 2 of these have blue color. So if I am selecting red, then the probability of finding red will be, because total number of red is what? This should be, isn't it? This should be 3 by 4. I don't know why it's writing down. This is 3 by, oh, sorry, I understand what it means. So the probability of finding red will be in first one, 3 by 5. But now in the second experiment, if you look for, the total number of red balls will be 2 from out of 4 balls, because number of balls are reduced in that, in the second experiment. So if you select blue ball, then probability of finding blue ball in the first trial will be 2 balls out of 5. So it means the rest balls of blue balls, how much will it be in the second experiment? If I look for the blue ball probability in this case, so this will be 1/4, because I'm not putting that ball again into my sample space. This is what all it explains, this picture explained. So for example, if we have 2 blue and 3 red marbles are in bag, so what is the probability of B and blue marble and red marble? Because these are, if these are independent events, if you are putting back, if you are putting these marbles back into your bag, so then what will be the probability if these are with replacement, like you are, these are independent events. So probability of blue and red. So this is the first experiment, and this is my second experiment, probability of finding a red marble. So if these are independent, so then you are writing it down, probability of finding blue balls multiplied the probability of finding red marbles. So let's say in the first experiment you find out, so I'm going to write it down like this. Let me make some, not this one, sorry. Okay. Let's say this is the number of balls. If I am finding probability of blue ball, so this will be, so this is like my blue ball. And if you select 1, so this is my, so how many balls, if I am finding blue, so this will be, because you are taking it out, so the rest will be 1 by, so the rest will be my 4 balls. Rest are 4 balls. So probability of finding blue is 2/5. So if you are finding in this one probability of finding red ball, so this will be 3/5. So in the first experiment, I took blue marble and I'm putting it, sorry, in the first experiment, I am finding the blue marble, which is 2 in that, total number of bag, total of number of bags are 5. So this will be 2/5. And I am in the, after first experiment, I'm putting that ball again into my bag. So the total number of balls again remain the same, which will be 5. And in those, in these, in this bag, again, I'm looking for the probability of finding a red marble, which is total number of marbles are 3 overall, divided by total number of choices I am having, which is 5. So this is what all it has written here, 3/5. But if I'm doing without replacement, so what will happen? So I'm looking for probability of finding a blue marble in the first experiment, and then I'm looking for finding a probability of red marble. So then you are using the formula again, probability of finding a blue marble multiplied by probability of finding a red marble given the blue marble has already happened. So in the first experiment, you found the probability of finding a blue marble. So in this case, if you take 1 blue ball, so how many balls I am having left in it, which is 4 in that. So probability of blue marble will be 2/5. But when you do the second experiment, probability of finding a red marble out of such that, or given that probability of finding blue marble has already happened, because I did not, after selecting the blue ball, I did not put this ball back into my bag. So the total number of balls I had 4, and those 4 balls have 3 red and 1 blue. So this is why if you are looking for red ball, so this is 3 out of 4 balls. So this is why it is being affected by the first experiment, just like the deck of cards I have done an experiment. So this is another example with replacement and without replacement. You have to look for that. So what it says, a bag contains 3 red, 2 blue, and 4 green marbles. So it means total number of balls will be how much? 3 plus 2 plus 4. So which will be 9. Total number of balls I am having 9. If you are doing with replacement, you are looking for probability of finding a green ball and probability of finding a blue ball with replacement. Because these are independent events, because you are using with replacement, so it means you are looking for probability of green ball multiplied by probability of finding blue ball, because this has nothing to do with the first experiment, because it is with replacement, you are putting back the ball into the bag of marbles. So then you need to look for what is it, are these probabilities, how many balls I am having which are green. So these are 4. So 4 out of how many balls I am having? 9. You are multiplying it by probability of finding a blue marble. So how many blue marble I am having? Which is 2. So total number of balls are 9. Then you simplify it. So this will be 8 by 81. So if you are doing without replacement means you are not putting back that marble in your bag. So it means number of sample space will be less. After first experiments, the total number of marbles will be from 9 to 8. And second experiment and third experiment, if you go for, then it will be 7, and then so on, reducing and reducing. So let's say we are looking for probability of finding a green marble and blue marble. So what it will be? So it means you are looking for, these are independent events without replacement. You are doing probability of finding a green ball multiplied by probability of finding a blue ball, given that finding green has already happened. So it means in the first experiment, what is the probability of finding green? Which is 4 by 9 multiplied by probability of finding a, but after finding that green ball, I'm not putting back into my sample space. So the rest of the balls will be 8, from 9 to 8, second experiment. So in the second experiment, if you are looking for probability of finding blue, so this will be how much? So how many blues I'm having? 2 by 8, because that green marble I did not put back into my bag. So this is how you will look for. So this is what you can, the second one you can do it easily. Let's go for third one, which is interesting, because you are doing 3 experiments altogether. Probability of finding blue and then blue and then blue without replacement. So how many total number of blue balls I'm having? Which is 2. So if you do first experiment, probability of finding a blue, which will be 2 divided by 9 multiplied by second experiment, and you are not putting back into your sample space. So in the second experiment, if you are looking for probability of finding blue ball, so what it will be? 1 out of 8, because that blue ball I took it away already. So if this ball is not anymore in the bag, so if you are looking for third experiment where you have no blue balls, so how many blue balls I'm having? 0 out of how many? 7. So if you multiply all together, so this will be 2 times 1 times 0. So the denominator will be multiplying with each other. So this will be, because due to this numerator is 0, out divided by anything, it will be 0, right? So this is giving you 0. So it means here the probability of finding blue after blue and after blue, it is 0. Similarly, if I'm going for look for some king from the deck of cards, total number of king I am having, which is 4. So if I ask you like finding a probability of queen from these deck of cards, queen, and then after, and then queen, and then queen, and then queen, and then queen. 5 times I have to look for to make it 0, because total number of queen cards I'm having 4. So this is all what is happening here. These are the examples questions I'm giving to you. You have to look for that what will be their probabilities, dependent and independent. So in the first experiment, this is for rolling a die. So you know that when you roll a die, so this gives you independent events. So then you have to look for, and the next one is for without replacement. Another thing which makes our work very easy for finding multiplication rule or for finding the conditional probability, which is tree diagram. If you look for tree diagram, it is very easy for you to calculate the probability of like multiple events happen. Then how can you look for the probability? So two things we have seen so far, one is with replacement and one is without replacement. With replacement means that if you do some experiment from the number of cards like we are having, and I'm putting back that card into my sample space, so the number of total samples will remain the same. And without replacement mean when you do some experiment and you are not putting that card back into your deck of cards, so this is going to reduce your number of sample space. So it means it is being affected the second experiment. So let's have a look with the tree diagram. Here is, I have an example that Jenny has a bag with 7 blue balls and 3 red sweets. Sorry, I am having this ball. So 7 blue sweets and 3 red sweets in it. So he has a bag which has total number of 10 sweets. From those 10 sweets, he has 7 blue and 3 red. And she picks a sweet at random from a bag and then replaces it and then picks at random. So it replaces it. It means if she finds a sweet and then she is putting that sweet back in the bag and then picks at random another sweet. So how you will look for these kind of probabilities, like draw a tree diagram to represent this situation and use it to replace the probabilities that she picks. So the first experiment is finding 2 red sweets, and second experiment, two no red sweets, at least 1 blue sweet, so 1 sweet of each color. So how can you look for? If you look for tree diagram, this is what we will make. So here we start. So the total number of sweets we are having 10, 7 blue and 3 red. So let's say if she select blue sweet, so what will be the probability in the first trial, like probability of blue sweet 7 by 10. In the second one, if she finds probability of red sweet, so how many number of red sweets we were having? 3 out of 10. So this is my first experiment. I did my first experiment. Let's go for second experiment and let's see how we can make a tree. So far we have represented first trial. In the second trial, again, we have 7 blue and 3 red because she's not going to put back in the, so she's not like eating the sweets and she's just putting back again in the bags. So again, we are having blue and red options. So the total number of blue balls in a blue sweets, what we are having 7 blue sweets. So let's say if she select blue, then probability of finding blue will be 7 out of 10. If she picks red, so that will be 3 out of 10. And because we are making branches, tree has a lot of branches, we are making branches. So in the first trial, we had 2 options, blue and red. With blue, we have again 2 options, blue and red. And in the first trial, we have red also. And with that red, we have again 2 options, blue and red. So we are looking for that one. So from red, we are looking for, if from red, again, we are looking for further options. If she again picks a blue, so that will be 7 out of 10. If she picks red, so that will be 3 out of 10 because this is with replacement. She is not eating it. She's again just putting back into the bag. So if you look at closely, so you will see here, we are making some sequence. You can see a pattern in these 2 experiments together. If you look for, let me use another highlighter so that I could look for. If you use for this branch, let's say this one, let's see what it gives. We are looking for probability of finding blue and then probability of finding blue in the first one. Let me use another highlighter to make it clear. So the first one is again coming from probability of blue, and the rest is after blue, it is going to red. So this branch is giving you, first experiment was looking for probability of blue. And in the second one, she is looking for probability of red. And if we look for the from the first experiment, let's say we are going through this branch, first one. So what it will give you, probability of B and probability of B. So this is our probability of B and then probability of B. If you look for second, let's say this one you are looking for. So first one, it is coming from blue and then red, blue and then red. So first was probability of blue and then probability of red. So it means total number of experiments we are having, like after making branches after second experiment, how many choices we are having? 4 experiments we are having total. So if you look for their probability, so this is how we will look for. So BB, this is what it says, outcome that I'm writing probability of B and probability of B. This is how it will writing down. First branch is giving me BB, second branch is giving me BR. So I'm writing it down in different symbols. So it means 4 total number of sample space we are having. One is blue, blue, one is blue, red, one is red, blue, and one is red, red. So if you look for their probabilities, because this is with replacement, probability of finding blue and probability of finding blue, 7 out of 10, 7 out of 10. You are just multiplying it. It is giving you 49 out of 11. Probability of finding second experiment, blue, red, in it, probability of finding blue times probability of finding red. So this is giving you 21 by 100. Third experiment, red, blue. So because this is with replacement, again, these are independent events. It has nothing to do with the second one. So it is going to give you you are just taking the products of these two probabilities. So probability of finding red, which is 3 by 10. And then you are looking for probability of finding blue, which is 7 by 10. You are multiplying it. It is giving you 21 by 100. Similarly, you can do for red, red. So this is giving you 9 by 100. One thing is very important here for you to calculate that whether you have done these experiments correct or not, to make sure that whether you are making those branches correct or not. If you add, this is very important, listen carefully. If you add these all 4 probabilities, like you are adding 49 by 100 plus 21 by 100 plus 21 by 100 plus 9 by 100, then it has to be 100 by 100. So if it is it 100 by 100? Let's calculate it. This is 42 plus 9, this is 50 and 50. So this is making 100 out of 100. So it means the branches you made, it's absolutely correct. You have nothing to do, you didn't do any kind of mistakes. So your experiment is, your tree diagram is correct here. So now you can look for something. What was the question? The question was, you have to find the probability of 2 red sweets. So which experiment has 2 red sweet? The last one, RR. So this has probability 9 by 100. If you make this diagram, once you make this diagram, then I bet you every question is very easy for you to find out for the conditional probabilities. So, but you need to make sure whether your experiment is conditional or unconditional. So next question, let's say what she looks, no red sweets in the second one. So no red sweets, it means it has to be blue, blue. Blue, blue is the only experiment that has no red in it. So that experiment, so that probability is 49 out of 100. So the next one is at least one red or at least one blue. What she's asking? At least one blue. So it means at least one blue. So this is the third sequence, fourth, and sorry, not the first three. The first three has at least one blue. At least one blue means that at least has to be one or more. So it could be blue, 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 red, and red, blue. So you have to add all of these first three together, like 49 by 100 plus 21 by 100 plus 21 by 100 is giving you the probability of finding at least one blue. So, and the last one, what it is asking you, one sweet of each color, like it has to be blue or red or blue. So there are only two options you are having, B, R and RB, which is blue and red and blue. So these have their probabilities 21 by 100 and 21 by 100. When you combine it together, it will be giving you 42 by 100. So this is the probability of finding at least, sorry, each of those colors in it. So this is what, how you will make the tree diagram. Uh, this is out for explanation that I've already made on the previous slide. So let's look for without replacement, how we can make the experiment for without replacement. Here's an example. Suppose we have 5 balls in a bag. They are identical except the color. Like one is red, one is blue. 3 of the balls are of red color and 2 are of blue color. You are instructed to draw out one ball, note its color, and set it aside. Like you have to take one ball, what is the color, find it out, and then take it aside. So throw it in the bin. So then you are to draw out another ball from the second experiment and then note its color. So what are the total outcomes you can have from the experiment, and what are their probabilities of each outcome? It is just like as the previous one, but here you are using without replacement. So this is why you have to use the first definition, probability of A and B, which is equal to probability of A times probability of B, given that probability of A has already happened. So this is the experiment. This is the formula we will be using for the product of two probabilities. So let's see, have a look. So first trial, this is the first trial. We have 5 balls. I am picking probability of blue if we are choosing blue. So what could be the outcomes? If she picks one ball, let's say it is blue. So the probability of blue in the first trial, it will be 2 by 5. And if she picks red, so then the probability will be 3 by 5. Keeping it in mind that after selecting this ball, she is throwing that away. She is throwing that away from the bag. So it means the rest of the samples will be this one. Like if she select blue ball, so the rest of the blue ball will be 1 and total number of balls will be 4. If she's selecting red ball, then the total number of balls will be 4, but the red ball will be 2 because it is reducing the amount. This is my first trial. And in the question, it has mentioned that there were 2 trials, that you have to again select the color and then you have to find out how many outcomes. In the first experiment, she said just take the pick the any ball, note it down and set it aside, and then do an experiment and then look for total number of outcomes. So this is my first trial. After my first trial, this is all is happening. This is the outcome it looks like. So if you go for second trial, this is my probability of blue in the first, and this was my probability of finding red. So again, if you choose blue, so there are again 2 possibilities. You can either choose blue and you can choose red. So this till here, it is my first trial. So in the second trial, what is the outcome? So second trial, we have total number of options. If this she's selecting blue, then probability of finding blue is 1 by 4, because given that probability of B has already happened, this is why it is 1 by 4. Did you see that how it is being affected, the second one, that it is 1 by 4, not 1 by 5, because given that the probability of blue has already happened without replacement. So if she picks red, so what is the probability? Probability of red we are looking for. So this is 3 by 4. So it means from first branch, we are having 2 options, probability of blue, blue, and this is blue, red. And then you have to look for second branch from the first trial. So the second branch was coming from red. So after picking the red, you have 2 options, probability of finding the blue and probability of finding the red ball. So if you look for probability of finding a blue ball, because there are 2 balls in there out of 4, so this is what you are writing. Same as we have done for the deck of cards or for the die we have done for. So probability of finding red without replacement. So this is because we are having 2 balls in here, red balls out of 4. So this is what we are writing. So it means from the second branch, we are having, how many options we are having? Red, blue, and red, red, right? So let's see what it gives us. So in the first trial, blue, blue, what is the probability? Blue, first trial blue was 2 by 5. Second trial, you did finding the blue, which was 1 by 4. So it means this is, if you simplify it, this is 1 by 10, isn't it? So blue, red, if you look for, blue was 2 by 5, red is 3 by 4. So it means this is how much? If you simplify it, 3 by 10. If you look for red, blue, so this was first experiment 3 by 5, blue was 2 by 4. If you simplify it, so this is giving you 3 by 10. Again, you look for red, red. So what are the options? What were the probabilities? 3 by 5 times 2 by 4. You simplify it, this is giving you 3 by 10. 3 by 10. Again, coming back to my point, how you can look for that your experiment is correct? You have to add all of these options, finding all of these options. So what are the options we find out? What is the blue probability, what it is? 1 by 10, blue, plus blue, red, what was the probability? 3 by 10, finding the probability of red, blue, 3 by 10, finding the probability of finding a red, red, which is 3 by 10. When you take the LCM, find it out, this will be 3 plus 3 plus 3 because denominator is the same. So LCM will be same 10 and you are adding all these together. So this will be 10. So it means 10 by 10. My experiment is correct. Making this tree diagram is absolutely correct. So these are the options we are having. So what was the question? Question was, it was asked, what are the outcomes of the experiments and what is the probability of each outcome? So what are the outcomes we are having? Blue, 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 red, blue, and red, red. These are the outcomes. And well, these are the probabilities that we have found, find out how it is. If I'm going to ask you, what is the sequence? How many sequence of having at least one blue? So what will be the answer? How many sequence of experiments having at least one blue? So it means you have to look for those experiment which has at least one or both has blue. So there are total number of 3 sequences, blue, 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 red, red, blue. So the answer is 3. One is question is that you are looking, I'm looking for the sequence. How many sequence? Like, do you understand my point that blue, 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 red, red, blue? So this is the one sequence I'm talking about. So if I'm going to ask you, find the probability of finding at least one blue, then you have to count those count those probabilities, then you have to look for. I can ask you that what is the probability of finding at least one blue? So then you have to add this one, blue, 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 red, and red, blue, and add this together, and that is something else. Sequence is something else. Probability, finding probability is something else. Sequence is that how many experiment has blue, blue at least. This is what we are looking for. So this is without replacement experiment. Same thing. Explanation I have already done. Okay. So sometimes it happens that finding the probability for successive trials, it's very hard for us. Very, very, very hard for us. Like if I'm going to ask you, what is the probability of finding 6 in 1,000 trials in rolling a die? 1,000, like it's a lot, right? How many times you have to do, how can you calculate it, and how many times you have to multiply it? This is very difficult. So this is why we can use complement rule. Do you remember last time we have discussed a complement rule of probability, that probability of finding an event A happening plus probability of finding A is not happening, this gives you 1. So if it is one thing happened, then second has to happen. So that thing we are going to use. At least one means, so For this thing, you need to know the meaning of at least one. At least one means that you have either one, it starts from one, or it could be two, three, four, or many you can have. So this is what at least one means. So complement of at least one, if you take the complement of at least one, so it means it's that was starting from one, so it has nothing in that. So if you take the complement of that, this is nothing. So this is how you will write it down. Probability of finding at least one is equal to probability of finding none. It's just like we have used last time, if you remember, probability of A plus probability of A complement. This is equal to 1. Here we are going to use the same rule. Probability of at least one, it means the complement is that has nothing in that. So if you add them together, this is giving you 1. This is what we are going to use it here. Let's say in this example, we are flipping a coin 3 times. What is the probability of at least one head? So here it is. So if I ask you to do it in a random way, like normally, in the first trial, I'm looking for head. So, and second trial, I'm looking for head. Third trial, I'm at least looking for one head. So 3 times I'm going to flip the coin. So I will have to find out the number of samples. Like let's say in the first 3 trials, first 3 flips, it can happen we have head, tail, tail in the first 3 tiles. If you look for, we also can have in these 3, how many options we are having? We can have head, tail, head, or we can have head, head, tail, or we can have all head, head, right? Or we might have this thing that in the first trial we get, in the first flip we get tail, and then we get head, and then we get head. And the second, it can happen, it starts from tail, and then we get head, and then we get tail. And then we get for, it also can happen that you have tail, tail, head, or you can have all the tails. This is the options you are having. Now we are looking for probability of at least one head. At least one head means that the sample spaces which has either one or it could be more heads in that. So how many it has? In the one we have, first one we have at least one head, head, tail, head, at least one head, 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 tail, at least one head, 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 at least one head. So tail, head, head, and tail, head, 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 tail, and tail, tail, head. So these are all the total number, how many experiment has head, 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 tail, 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 head, something like this. So the total numbers, the total sample spaces we are having, which has at least one head, is 7 from 8. So this is 7 out of probability of finding at least one head is 7 out of 8, because we have 8 options. Why not we look for probability of finding no head? So probability of finding no head means that has no head, so all has to be tail. So there is only one option that has no head in that. So probability of finding no head is only 1 in this overall sample space. So 1 by 8 in our total number of sample space, which has no head in that. So if you use this rule that I have discussed already, probability of at least one head, it means probability of having no head, and you subtract it from 1. So if you subtract probability of at least one head, 1 minus probability of having no head, 1 by 8, isn't it giving you 7 by 8? So the answer is the same. If you find 1 minus probability having no head, the answer is the same. Instead of looking for each sample which has at least one head and you count it down, this you are looking for 3 times, that is fine, you can make it. But what if I ask you 4 trials? So 4 times you have to look for, so then you will have 16 number of sample spaces. What if it happens that I ask you to find out 5 times coin, you're flipping the coin and look for at least one head, then you have 32 number of sample spaces. And if you look for 5, then it will be 64 samples, and it will huge and huge and huge. Like, so the probability of finding at least one head will be complicated to you. So let's have a look how we can solve it out for the bigger number of trials or bigger number of experiments, how we can do that. If you flip the coin in this example 20 times, what is the probability of finding at least one head? So you are going to use, again, this rule, probability of having at least one head equals to 1 minus probability of having no head. So there is only one option you can have which has no head, that each experiment has to have only tail in that. So tail, 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 tail. This is the only option in overall sample space where you have no head in that. So it means 1 minus probability of finding tail and tail and tail and tail and tail and tail and so on. How many times? 20 times you're looking for. I have to write in another way, like I have been using in this course, like probability of finding tail and tail and tail. Remember, and we are using for successive trials here, not for addition we are using. So and tail and so on. How many times? 20 times, because you are flipping the coin 20 times in that. So this means, because these are independent events, so probability of finding T, again, we're using the product rule, multiplication rule, probability of finding T, and again, probability of finding T. How many times I have to take the product? Which is 20 times I'm taking the product. So this is 20 times, because you are flipping the coin 20 times. So what is the probability of finding tail, one single tail? 1 by 2. Again, second, in this one, I'm looking